Hello viewers, welcome you all. In this lecture, I am going to take the next unit of solid state physics, and it is free electron theory of metals. Right? Free electron theory of metals. Right? In this lecture, I am going to take up some important points of this unit, this chapter. This theory, free electron theory of metal, was developed to explain the electrical property of solids, right? And it was, developed from the beginning of 20th century, right? First of all, in 1900, right? Paul Dirac, Paul Drude, not Dirac, Paul Drude, who was a German physicist, right? He, developed this theory, which was later on modified by Lorentz, right? So we also call it as Lorentz-Drude theory of metals or Lorentz-Drude theory of free electron gas, right? So it was, basically assuming the electron inside the solid as a gas of, molecules which are moving freely inside the that material, right? The situation has been made analogous with the gas of molecules contained inside the container, right? The main thing that was the assumption foundation of this theory was free electrons. So according to this theory, you can see here a picture, right? I have drawn. According to this theory, free electron theory, all the solids, right, they consist of a positive ion core, right, and the cloud of electrons which are tightly wound to that positive ion core, and freely moving electrons which are present in either the valence band or conduction band. These electrons, either one or two, they are considered as a completely free, right, and they are wandering inside the that solid, that material. You can see here, this red circle is a positive ion core with tightly wound electron cloud, but these green dots are free electrons. You can see here, these free electrons are present everywhere inside the material. Now according to this theory, these free electrons are totally free. They can go anywhere inside this metal or this material, except they can't escape from these boundaries. They can't come out, right, because of the potential barrier existing at these boundaries. I mean, they are confined inside this material. So the situation is analogous to a gas, ideal gas contained in a cylinder, right, where the gas molecules are completely free to move, right, inside the cylinder. So that's why we are calling it as a free electron gas, right? Free electron gas, right? So this free electron gas is quite similar to the ideal gas contained inside the container, but there are some difference between these two, like the concentration of free electron gas is around 10 raised to power 29 to 10 raised to power 30 electrons per meter cube, whereas the concentration of gas molecules inside a container is around 10 raised to power 24 molecules per meter cube. So you can see the concentration of the electron gas is very, very high as compared to the concentration of gas molecules. The other thing is the gas molecules are neutral. What here, the electrons that are moving inside the material, they are charged particles, but all their interactions has been ignored in this theory, right? It is assumed that they are not interacting with each other. They are just moving from one place to another place inside the metal, but they are not capable of coming out of that metal, right? So this is the foundation of this free electron theory of metals. It was initially proposed by Paul Drude in 1900, but later on it was modified by Lorentz. So that's why we also call it as a Lorentz-Drude theory of metals. And this theory was proposed to explain electrical and thermal properties of different solids, right? So, and it was successful in explaining various properties of the solid, like it is capable of explaining Ohm's law, right? It is capable of explaining the electrical conductivity, right? It is capable of explaining thermal conductivity. It is capable of explaining Weismann and French law. So many of the properties of the solids has been explained on the basis of this free electron theory of metals. We also call it as a classical theory of free electron theory of metals, right? So I'm going to explain one by one all the things that has been explained by this theory. For example, this theory is capable of explaining Ohm's law, that is J is equal to sigma E. We know very well this is the vector form of Ohm's law. It is capable. It is also capable of explaining B is equal to Ri, right? Or we can say I directly proportional to B. It is also capable of explaining this, right? It had explained. I'm not going into all those details, but it explained this one, right? J is equal to sigma E. It also predicted the value of sigma. Sigma is what? It is electrical conductivity, right? And according to it, we know very well sigma is equal to Ne square tau upon 2m. Here tau is the relaxation time. So this can be written as sigma is equal to, if I put the value of tau, tau is relaxation time, so we can take it lambda upon B average, right? Lambda is the mean free path of electron between any two successive collisions, right? And B is the average velocity of the electron inside the given material, right? So if I put here, then this equation will become Ne square lambda upon 2mb, right? So in this case it get modified. Now I can even further modify it by taking half mb square is equal to 3 by 2 kT, kinetic energy of the electrons. Just like we are assuming that this kinetic energy of the electron is equal to their thermal energy. So if I put it here, then it will become Ne square lambda B upon 6 kT. Here B is average velocity, right? You can see here. So this is the expression for the electrical conductivity of the metals, right? So this expression has been verified experimentally. So it means this theory is capable of explaining the electrical conductivity of metals, and it is verifying the Ohm's law, right? It also explains the thermal conductivity, right? Thermal conductivity. So we know very well that thermal conductivity coefficient K is equal to half N B lambda and small k, right? Here small k I can write it Boltzmann constant. So according to this theory, Lorentz-Drude theory, the thermal conductivity of the metals capital K is equal to half N. N means number of free electrons per unit volume, B is velocity average, lambda mean free path, Kv is Boltzmann constant. So we know very well the coefficient of thermal conductivity. It is defined as Q is equal to K dt upon dx. So from here we have calculated this K value. I am not going into all that. Capital K, right? It is equal to this. We have to only remember these expressions for electrical conductivity and for thermal conductivity. Do not go into all these derivations, because examiner can ask you that what is the value of electrical conductivity or thermal conductivity. So these are two expressions given here. We have to remember them. Now it comes the important law that we call Weidmann and French law. Weidmann and French law. It is very, very important and usually asked in the exam. So according to Weismann and French law, the ratio of the thermal conductivity to electrical conductivity is always proportional to the absolute temperature of the material, right? This is the Weismann and French law. So you can prove it by simply putting the value of K and sigma, and you will see when you put the value of K and sigma, that's why I was saying that we have to remember these expressions. So when we will put these two values, we will get K upon sigma is equal to 3 small kb upon E, right, whole square into T. Now kV is Boltzmann constant, A is electronic charge, 3, all these things are constant. So K upon sigma directly proportional to T. This is the Weizmann and Friend's law, very, very important, but it is derived by using the thermal conductivity expression and electrical conductivity expression. So these are some important successes of this classical theory of free electron gas, right? We call it as a classical theory because in developing this theory, classical models of the physics has been used, right? No quantum result has been used. So we also call it as a classical theory, right? So important points once again I am recalling. First of all, why we are calling it as free electron gas, right? What is the concentration? What are the differences between two, right? Then Ohm's law, electrical conductivity and thermal conductivity, right? Now, later on, as I told you that this theory is capable of explaining certain features of the matters, but it has many drawbacks. Like it is not capable of explaining why certain materials are behaving like conductors, certain are insulators, certain are semiconductors. It is not capable of explaining the concept of Fermi energy. It is not capable of explaining, right, the magnetic properties of the material, specific heat of the solid. All these things were not explained by this theory, right? So in order to explain all these things, a new theory was developed that we call as a Sommerfeld quantum theory, right? Sommerfeld quantum theory of free electrons. Again, the concept is same. Sommerfeld in 1928, right, proposed this theory, but the basis or foundation of theory was again same, that the electron are totally free inside the given material and they are moving inside a potential barrier just like this, right? They are not able to escape from this boundary because of the existence of the potential barrier, but otherwise they are free. But the Sommerfeld applied quantum results, right? That is Fermi-Dirac statistics, right? FD statistics to explain the behavior of a free electron gas. Now, in order to understand the Fermi-Dirac statistics treatment of electron gas, if you want to go in details, you can go to my lecture, right? That is, I am also giving the link of that lecture in this video, but you can go to that in my course Statistical and Thermal Physics. You can learn in details that how this free electron gas treatment is done by Sommerfeld by using Fermi-Dirac statistics, right? So in Fermi-Dirac statistics, I am coming to some important points. What he did, he simply considered the problem of a particle in a box that you have learned in quantum mechanics, right? And it is assumed that I am drawing it here. It is the length, right? 0. We are considering one dimensional box, right? Inside the box potential is 0, but at the boundaries it is equal to infinite. So that's why the electron is present inside this one dimensional infinite box, right? And it is not able to escape from the box because of the presence of these boundaries at x is equal to 0 and x is equal to L. So this is the treatment that is done by Sommerfeld by assuming the same basis as it was considered by Lorentz and Drude, but he applied the Fermi-Dirac statistics and a quantum approach in solving the problem, right? Now the electron is present inside the box, right? And inside the box, the potential is equal to 0, but at the boundaries, potential is infinite, so electron cannot escape from there. So by using this theory and Schrodinger wave equations, all these things are mentioned in that lecture. You can go if you want to go in details. He derived the expression for the energy. That is very, very important. En, energy of the electron, is equal to h cut square upon 2m into n pi upon L whole square. Here one thing we have to remember, that this treatment of the Sommerfeld is for free electron gas in one dimension, right? Remember it. It is for getting the things simplified. We can extend this approach to 3 dimensions, right? What I am considering only free electron gas in 1 dimension, and this is the expression for the energy of the electron inside the box. Very, very important result, right? Many questions are framed from this expression, right? H cut square upon 2m n pi upon L whole square. Okay? M is the mass of the electron, n is quantum number, quantum state, and it is given as n is equal to 1, 2, 3, so on, right? Quantum state of the particle, right? And L is the dimensions of the box, right? So we can see from here that the energy of the electron is directly proportional to n square, right? It is inversely proportional to L square, right? The other things are constant. So you can be asked a question on the dependence of the energy of the electron inside the box on different factors, right? So we can calculate it. Similarly, we have calculated the expression for the wave function, right? And the wave function is psi n of the electron 2 upon L under root sine of n pi x upon L. This is the expression for the wave function of the electron inside the box, right? So we can plot this wave function. I'm plotting this wave function here. Right, you can see here. So this is the box 0 L, right, x, and this is the wave function psi n. Now you can see the wave function, right? We know this is the wave function that is plotted here, and for the first case, minimum value of the energy, what is the minimum value of energy? E1. E1 is also known as the ground state energy, and it will be h cut square upon 2m into pi square upon L square. So this is n is equal to 1 state, and the corresponding wave function is plotted as, right, this one. Similarly, for n is equal to 2, you have the wave function of this type, right? N is equal to 2. For n is equal to 3, you have the wave function this type, n is equal to 3. So we have to remember all these graphs, all these cases, that what is the n is equal to 1 state or ground state, n is equal to 2 state, right, n is equal to 3 state, and so on. So this is very, very important. This is psi 1, this is psi 2, this is psi 3, right? Now if I want to find out the probability of the existence of electron inside the box, then probability we know very well from the quantum mechanics. It is dependent on psi star. So if I plot that probability psi star, then what I will get? I will simply get, I'm doing it here, you can understand, we are simply getting 1, right? Means the probability is maximum at the center. for n is equal to 1 state. The probability of locating of the electron is maximum at the center of the box. But when we go n is equal to 2 state, then we get this type of graph. Means the probability of locating electron at the center is equal to 0, but it is maximum at these positions. You can see it is, I think it is L by 2, right? So it is L by 4 and it is 3 L by 4. So probability is maximum at L by 4 and 3 L by 4. Similarly, when you will go n is equal to 3 state, you will get 3 nodes in this way. Probability 0 here, maximum in this way. So the question are asked from here, from this graph, that where the probability is maximum, where the probability is minimum, right? Which is the what is the value of energy in n is equal to 1 state, right? Ground state, or we can call it as minimum energy state, right? So we have to know very clearly these graphs, the graph of wave function and the graph of probability. The one more thing that we got from this expression, that is the energy levels of the particle or electron inside the box, they are not equally spaced. For E1, I can say E1 is equal to E1, but E2 is equal to 1 what? If you look at this, because it is directly proportional to n square, so it will be, when n is equal to 2, it is 4 E1, n is equal to 3, it is 9 E1, n is equal to 4, it is 16 E1. So you can see they are not equally spaced, but as we are moving up and up toward the higher energy, the gap is increasing. So this question can be asked, right, about the these different energy levels. So this was the treatment of Sommerfeld, right? He also calculated the value of the Fermi energy in one dimension. What we have to remember, that we are taking the case of Fermi energy in one dimension. So according to Sommerfeld, Fermi energy in one dimension, I am writing one dimension, this is energy Fermi and one dimension. So it is according to this model, h square upon 2m into capital N upon 4L whole square. Here capital N is equal to 2 times N, right? Here NF is the Fermi, the quantum number corresponds to the Fermi level, right? That NF, right? So we know very well why I am taking N. N is the number of electron. Why I am taking it equal to 2 into NF? Because we know only 2 electron can accommodated in one level. So if NF is 4, I mean it is fourth level, Fermi level is fourth level, then the number of electrons will be 4 into 2, 8. So this is the expression for Fermi energy. Similarly, it also calculated the value of density of states. Density of states means a number of allowed energy states per unit energy interval. Number of allowed energy states, dN divided by dE. So for one dimensional case, it is found that dE, density of state, is equal to 4L divided by H into M upon 2E power 1 by 2. So we can see that from here, that the density of state, L, N constant, M constant, right? No, it is not N, but it is H, sorry, H, Planck's constant. So L, H constant, M constant. So it is inversely proportional to 1 up E power 1 by 2, right? So we can see from here, right? So this is the density of state in one dimension, and this is the Fermi energy in a one dimensions case, right? We have also calculated the average energy, right? Average energy in ground state. So I am writing it as a E0 naught. So according to this model, it is equal to 1/3 of the Fermi energy. So we have to, but we have to remember one thing in all these expressions, that it is 1D, one dimensional case. Average energy of the electron is equal to 1/3 of the Fermi energy, right? Now I am applying this Sommerfeld model for the three-dimensional case. So when you will go for the three-dimensional case, then when you will find the expression, three-dimensional means we are now considering this a three-dimensional box. So the energy expression En. Now it is N1, N2, N3. It is equal to h cut square upon 2m into pi square into N1 square from A square plus N2 square upon B square plus N3 square upon C square. So this is the expression. Here N1, N2 and N3 are the corresponding quantum numbers along the three directions. A, B, C are the dimensions of the box along these three axes, right? If the box is cubic, then A is equal to B is equal to C. So we can take then it common. So it will become h cut square upon 2m, right? Pi square upon A square into N1 square, or we can call it Nx square plus Ny square plus Nz square also if we take it as Nx and Y. So you can see here, you can calculate Nx, Ny and Z. This is the expression for the energy, right? Now based on this expression, you can be asked many questions, right? That what is the degeneracy of this state, what is the minimum energy of this state, right? So all these things can be asked from here. So you have to practice all these things based on this expression, right? Similarly, I can write down the expression for the wave function psi. Now Nx, Ny, Nz. So it will become, obviously we have under root 2 by a. So you will multiply under root 2 by a into under root 2 by b into under root 2 by c into sine of nx pi x upon a into sine of n by pi by upon a, right? Sine of n z pi z upon a. Not a, sorry, here it will be and it will be c. So this expression is analogous to this expression that I have written n pi x upon l, right? So here nx pi x upon a, ny pi y upon b, and z pi z upon c. This is the expression for a wave function in the three-dimensional case, right? Now I am writing down the expression for the Fermi energy in three dimensions, right? We have calculated the value of Fermi energy in three dimensions, right? You can also refer to the actual lecture in the statistical and thermal physics where I have calculated. So EF, Fermi energy in three dimensions, that is equal to h cut square upon 2m, right, bracket 3 pi square capital N upon B, right, power 2 by 3. So you can see from here that the Fermi energy in three dimensions, usually question is asked from here, h cut, m, pi, all these are constant. So it is dependent on n upon v. N is what? Electron concentration, number of electrons per unit volume, right? Now number of electrons, sorry, in the given material. So you can see here that the Fermi energy is dependent on n upon b, right? Concentration of electron divided by volume, and it is constant for the given material, right? It means Fermi energy is an inherent property of given material. It does not depend upon the mass, length, volume, or other factors of the given material. It depends only on the concentration of the free electron, right? So if we have, suppose copper wire, right, of length 2 meter, right, and I have another copper wire that is of length 10 meter, then you can be asked that which one have higher value of the Fermi energy. The Fermi energy will be same in both the cases because the concentration of electron is same, n upon v is same. It doesn't matter if you increase the length. With the increase in length, n will also increase. So n upon v is always constant. So that's why the concentration of the electron is constant, and that's why the Fermi energy will not change. So that was about the Fermi energy, and it is the case of a Fermi energy in three dimensions, right? Now we have also derived the expression for the average kinetic energy, right? Average kinetic energy, and it was equal to 3 by 5 EF, right? It is the case of Fermi energy. in 3 dimensions. Similarly, we have also drawn a expression for the density of the states, dE, and we have to remember 3-dimensional case, it is equal to in this case B upon 2 pi square 2m upon h cut square, right, power 3 by 2 into e power 1 by 2. So you can see here that the density of the state is directly proportional to e power 1 by 2 in this case. Other factors are constant, right? So this is the density of state. This is the average energy at 0 Kelvin. Similarly, we also have calculated in case of Fermi-Dirac statistics average velocity at 0 Kelvin, right? And I think it was 3 by 4 BF. You can check it in going to that lecture. So this was about the free electron gas treatment by using quantum theory, right? Now I am coming to the last concept, that is specific heat, electronic specific heat. I told you in yesterday's lecture that the most successful model of the specific heat, that was a dy model, and according to that, at low temperature CV is directly proportional to T cube. I told you at that time that this model is valid, right, for most of the materials, but when we apply it to the metals, then it is not working properly there, right? So for the metals, this expression got modified, and it is found that for metals at very low temperature, the specific heat varies linearly with temperature. So it becomes CV is equal to AT plus BT cube. Right? This is the expression for the variation of specific heat for metals at very low temperature, AT plus BT cube. I am saying that at very low temperature, right, when the temperature become of the order of 0 Kelvin, then CV for metals becomes directly proportional to temperature. But when the temperature is slightly higher, then it is, right, directly proportional to T cube. Why? What is the reason? The reason is when the temperature is very low, then the contribution of the electrons in the specific heat becomes dominant, right? Because metals have free electrons, so they can also absorb thermal energy and they will generate thermal vibration phonons, right? So it means for that case, right, the electronic contribution in the specific heat will dominate. But when the temperature is slightly increased, then the contribution in the specific heat, because of the lattice vibration of the whole lattice, they will dominate, and then this factor will become dominant, right? So this is the expression for the specific heat of the solid metals, right? So we have to remember, you can be asked that what is the expression for the specific heat of the metals at very low temperature. So this is the answer. And again, at high temperature, CV is equal to 3R, right? Dulong and Patet's law. So we have to remember all these important points. This chapter, free electron theory of metals, is again an important chapter in solid state physics. Usually questions are asked either from specific heat or from this treatment, Sommerfeld treatment, or from the thermal conductivity and electrical conductivity. This graph, once again I am telling you, go through it, the plot of wave function and the plot of probability density, right? So this is all about it. So thank you very much.